Okay. Uh, it's 6 o'clock, and I guess we have 22 people, and probably that'll be it today. All right. Can I guys see my screen okay? I just start recording, so I hope recording the right screen. Okay, perfect. So, first of all, I want to ask have you guys have any issues about downloading SolidWorks? Okay, that's great. So I'm assuming everybody got their SolidWorks set up, and because today we're gonna do some SolidWorks stuff, and I'm gonna give you some recommendation how you guys practice at home, so you guys can just practice on weekend, and or watch the lecture recording on weekend. So do some self study. Okay, let's start it. Pretty much today we're going to do a PowerPoint. They're going to give you some introduction about some terminologies, and we're going to do a practice. And after the practice, we're going to do some SolidWorks modeling, and we'll call it a day. So let's see. So pretty much introduction, and this is the animation of the engine block assembly I showed you guys on the first week. And this animation is done by SolidWorks, which means after you guys construct the assembly, you guys can do the same thing, set up your own angle and set up the timeline and all that, and pretty cool stuff. And you can, show it off as one of the products you made in this class. And don't worry, I'm gonna post all the PowerPoints on Canvas. So, first of all, we're gonna talk about drawings, because like I said, all the modeling is just the feasibility check or spatial check when you build something, and the drawing is the key to produce it or manufacture it. Like whoever gonna machine it or make this part, they're gonna require a drawing. Without a drawing, doesn't know like how big that is and other dimensions. So this drawing is a flange, a very simple one. And to those of you who doesn't familiar with flange, which means this piece is supposed to have another piece to form a couple, and pretty much sometimes identical. So you bound these two pieces by 4 bolts and nuts or stud and nuts, whatever, the fastener. And in the middle, you have a pipe going through the hub. So the flange is a very safe, like leak tight way to connect 2 pipes or 2 nipples. So let's talk about it. This is isometric view. Pretty much this is just a reference to give you an overall idea how this flange look like. Without this, some people is a little bit hard to visualize because you only have all the I'll say the plane views or primary views. Let's start with the first one. This, we can call it a side view or front view, depends how you look at it. Let's just call it front view for now. You can see the dimensions are labeled, and then on the side there's a section view. The section view is for the cross section, and the cross section are labeled as A-A or A-A. And you can see from this view there is the leader line and like the line that cut off the cross sectional, and also called A and A. So when you see something like this, you go to another view to look for the section, and this is the line that they follow to cut the subject in half and show you what's inside of it. And this is the top view. So if you can imagine, is view it from that direction. So pretty much looking at the back side of the flange. And here it says detail B. So it's a detail view. Detail view is the view that pretty much zoom in for some small features because it's really hard to identify or indicate in its original view, which you can see a circle as a B. So the circle area is zoomed up by a scale 2:1. So that means is if those views are one by one, the sheet says is 1 by 1, right? And those doesn't really label the scale. So those are sheet scale is 1 by 1 and it's 2 by 1. So is zoomed in like twice, twice as big. And just to indicate the dimension of the chamfer. And you can see the chamfer has an overall length of 0.08 and degree of 45 degrees. So let's talk about dimension a little bit. First of all, I want to say, for example, this 0.08. Normally, industry would call it 80 thou, means 80 thousandths of an inch, or in term of if it's a millimeter, we just call it like 0.08 millimeter or so. But I believe in America, we're the only country that uses English unit. And I pretty much deal with English units most of the time, and let's stick with that. So this is called 80 thou, and this 0.5, you can call it half or 500 thou, like it's really up to you. Okay. So this 0.75 or 3/4 indicates the thickness of the flange. So pretty much is how thick the flange sealing surface is, and the 2.25 is the overall thickness or overall length of this flange. That also indicate how deep the hub is. 2.75 and 5.5, they're just the OD of the two sides. And we see this dimension, this 1.500 and plus 0.3 thou and minus 0. It looked pretty special, right? They look different than all of the other dimensions. The reason is because this is called tolerance of this dimension. So, for example, if some machinist machine the idea of the hub into 1.504, can somebody tell me if 1.504 consider a fault or is considered acceptable? Yep, everybody got the right answer. It's considered a fault. The reason is because the biggest it can go is 1.503. And same thing to the other side, the smallest it can go is 1.5. So pretty much the value on this dimension can only be 1.00, 1.01, 1.02, and 1.03, only the three values. And also this 4 times ½ inch means this hole is ½ inch in diameter and total of 4 places. So when you have identical feature, you can use either like some number times something to indicate that. So you don't have to label each individual one. They're gonna make your drawing look pretty messy. Or you can just say ½ inch in diameter and 4 places total, something like that, add an annotation so the machinist will understand. But if you have the holes in different size, for example, this one is 0.6, this one is 0.7, then you have to label them or define it individually because they're different. So this 4.25 is linked from the center of this hole to the center of the bottom hole. And it still gives a diametrical sign. is because it's not only telling you the distance, the center distance between these two holes, also is indicating these four holes are made by a circular pattern. So pretty much it tells you the both circle diameter, which is 4.25. That's why it has the diametrical sign on it. If it doesn't have the diametrical sign, you missed it or intentionally skipped it, that means these two holes are 4.25 inches away, and the other two holes are not regulated or not defined. The position of that two holes are not defined. Okay, so those are just some common practice to make your drawing look neater, and at the same time not over defining anything. Okay, so I want to talk about a little bit about the default tolerance. If you guys can see where my cursor is, the default tolerance has 4 lines. The first one .x and second one .xx, third one more x, and the angle. That means .x means 1 decimal place, and XX means 2 decimal places, etc. So let's bring up this example, 0.75. This 0.75, it has 2 decimal places, right? 7 and 5. And it's gonna fall into this category, in which the default tolerance is plus minus 0.030, which is 30th tolerance. So in this dimension, you don't have to indicate any tolerance because it's been regulated by the default tolerance. So let's look at this, the 1.5 diameter. The reason we want it to have its own tolerance is because we want this surface to be well controlled. So you can see the tolerance, the total tolerance from this dimension is only 3 thou. That's very small. So it must be very precise. But for the thickness, since we don't really care about thickness, or we don't care that much, and give a 30 thou tolerance, that's okay, acceptable. So also cheaper to make the part. So let's see. If this 1.5 doesn't have its own tolerance, what kind of tolerance it will have when we release the drawing? Anybody? Any more? Nobody want to take a shot? Yep, I see the right answer. Yes, so you're gonna fall into the third line because it has 3 decimal places, 500. So it goes into .xxx, and its tolerance reads plus minus 5 thou. So yep, so if it doesn't have its own tolerance, this part can go 1.505 or 1.495. Okay, I'm about to move on. Any questions so far? Okay, great. So let's talk about views. So first, we're gonna talk about lines and how many different type of lines are there, and what they're used for, or whatever. And what are the multi-views, what are they, how are they made, and when do we use them, and pictorial views, such and such. So first, edge lines. The same drawing being brought over here. The edge lines is are used to show an edge or border of the part. Okay. Let's go back to this drawing since I can make it bigger. Okay, let's talk about it. So this line right here, is it an edge line? Come on, people. Give me some response. Is this an edge line? The top one right here? Yeah, apparently it's an edge line, right? What about this one? Well, yes or no? It is an edge line, right? That's your bore. You have nothing, like, you really have nothing for that to not be an edge line, right? Yep, that's right. It's an edge line for something inside the part. Yeah, so it's hidden because you cannot see it from the side, but it is an edge, right? From this view. You just cannot see it because you don't have the X-ray eyes, but it is an edge line. And how about this? Right? Most people got right. It's not an edge line. This is the center line of the hole, or you can call it construction line, reference line, yep, through hole line. It's not an edge line. It just indicate this is a through hole and this is the center line. So pretty much when you see the isometric view, you can see some lines are solid, some lines are dashed, but you really need to identify it by your knowledge or experience, whether they're edge lines or not. Because sometimes if you make a very complicated part, it can be really confusing from beginning. So normally the practice is make a through, make a center line of a hole if it's a through hole. And that's why you can see from this isometric view, there are 1, 2, 3, 4, 5, total 5 dashed lines through like 5 circular holes. And same thing right here. You can't see the line going in and out of the hole, but you can see a little cross. That's how we indicate this is a circular feature, and that's the origin of the circle or the hole. Okay, so can someone tell me the little ring right here? You can see two circle are really close to each other. What are those little ring? What are this little ring? Yep, that's right. It's a chamfer. It's a chamfer in detail B. Yeah, sometimes it might be a little bit confusing because you will totally forget about there's a chamfer there, and it looks like, wow, why I have so many different edges. And when you introduce the detail B, you can see there's an edge right there, and this gonna make another edge when you see it from the top. Okay, I think it's pretty good. And now the hidden lines. Hidden lines are used much like edge lines. The difference is solid geometry covers up the edge. Yep, so we just talk about it. So sometimes they're still edge lines, but just invisible from the view. And sometimes they're just reference lines and doesn't really mean anything. But it's good to be there for your reader or audience better understand your drawing. And also the center lines is most likely for the circular feature. So it just reminds you there's a hole or there's a bore, and still help the audience better understand your drawing. Multi-views. Like the drawing we just saw, it has like 5 or 6 different views, right? 1, 2, 3, 4, 5. It has 5 different views. Okay, let's go back. So it's just terminology. Read it after I post it. Pretty much all you need is front, top, right. Because if you're making a simple geometry, the rear, bottom, left is just the another side of the front, top, right. So not necessarily to display L6. So most commonly you'll see 3 views and some detail view and some cross section and stuff like that. Unless, for example, something at the bottom has like an engraving or something, like some small feature, you have to show it because it's different than the top. And parallel projection, orthographic, all that just. So let's play this. Okay, the rest is just repeating steps for the 3 views. So you can see this subject, it looked like an L. L like also look like a hinge or something and has a hole on the bottom plate or bottom step and missing a corner on the top portion, and it looked completely different in its 3 views. The front view looked like a L, or we call it red view or whatever. It looked like a L, and the other side looked like a a symbol Word doc or something, and the top view completely looked like a hinge. So when you make the drawing of this part, you're gonna display 3 views and define them from there. And also, if you're a nice person, you're gonna put an isometric view, which is this view at the bottom corner. So tell the machinist this is how it looked like in final product. And parallel versus perspective. So this and that, well, why this showed up? Okay, so this and that are the different views of a same subject. This, you can see, is kind of like a rectangular piece, but the front is smaller than the rear. So when you see it from the back, you can see nothing because rear is bigger than front. It blocks it all. It blocks it all. And when you see it from the front, you can see the partial top and partial bottom. You can see the slopes. Some I'll say like optical example, right? Yep. So this is a comparison. So this indicates how important to draft your drawing in different views. And this is projection. Like how does it look on paper? Same thing from another orientation. And this from the top. And this is a summary of the previous 3 slides. Okay, projection lines. So sometimes you will have projection lines, but very rarely happened. But at this stage, it's good to help you understand how you make your views by using projection lines. So you can see anywhere it has an edge, they're pretty much a projection line indicates that, the same bottom thickness and, the same slope and same hole. So from this view alone, there's a through hole because it indicates from the top and bottom. And this miter line, this tells you that. Pictorial views, and these are just terminology. You can memorize it if you like, and I'll post it on Canvas. And isometric view, which you're going to be using a lot of time. Okay, any question about the slides? Okay, yeah, this is just very fundamental stuff. I guess like a lot of you already know this just by common sense, right? Okay, let's do some practice from 3D to 2D, because I know like for some people, they'll have a hard time that visualize 2D drawings into 3D subject. Okay, everybody, let me know in chat. The first one, this is a mix and match. Which one at the bottom is the first model drawing? Oops. No, you're supposed to give me a letter. Okay, most people vote K. Let's see. So top view is missing the right side. It has missing the right side, center notch. There's a center notch. And look at front, like missing the right side too. And the right side, right view is a big L and with a notch. Yep, that's K. And number 2. Okay, let's see if number 2 is L, missing the right top right corner and top bottom corner. So from this view, bottom corner is out and the top right corner is gone. And there's no notch. Yes, is L. Number 3. Okay, let's look at D. Number 3, same as number 2, missing the top right corner, and same as number 1, has a center notch. So D has a notch, check, that's a check, and missing the top right corner, that's another check, and from the right side, you see an L, yes, that's D. And what's number 4? Okay, number 4, probably gonna be a little bit easy because it's totally different configurations than all the others except for number 8. So you guys saying F, right? So pretty much missing the left side a little bit and also the right bottom corner. And from the top view, you don't have left side, you don't have no bottom corner, and then all the other views matches. Yep, that's F. And number 5. Yeah, number 5 is the easy one. It almost has one feature in there as a center notch, and yep, that's A. And number 6. Yep. Let's see. Missing the top left and center notch, missing the top left and the center notch. And yeah, it's the number 7. Right. pretty close to number 6. It's just notch and the missing part being replaced with each other. So the top notch and the right side corner, and yes, that's G. And number 8. Yep, number 8 is also pretty significant. Similar to number 4, missing the right side and also the little bit bottom top. Sorry, a little bit the top right. So top right is gone, and then the bottom right is gone. Yeah, let's be number 9. Yep, so the top notch and the right bottom side, and H, yeah, the bottom right, missing a big chunk, and the top notch, that's H, and 10. Yep, 10, number 10 is pretty obvious. The bottom, make it a square, so probably the only square on all those views is M. And number 11. The number 11, top left and bottom right, and J is missing top left and bottom right. That's J. And number 12. And the number 12, you need to even look at it. You have the C. That's the only option left, right? Okay, that's great. Anyone has any questions about this one? This was supposed to be your homework, and since I canceled all the homework, we just practice in class. No questions? Okay, so you guys are expert of converting from 2D to 3D now. Am I right? Okay. Okay, let's do some SolidWorks practice and we can call it a day. Yeah, it has been a long day for me. So sometime if I drifted or spaced out, don't blame me. Yeah. Okay, let me show something first. This is a flange that we have been studying the drawing of it at the beginning of the class in this PowerPoint. So this is a machine drawing and this is the actual part. You can see it looks the same as the isometric view, kind of like that, right? And I first of all want to introduce how this part has been made. So now we're gonna play with this blue bar. This blue bar is like I said during the first meeting, this above this blue bar, all the features are shown in your workspace. Below the blue bar, that means the features are inactive. Okay, and let me show you. Well, anyway, let's start from the top. Sorry, I forgot. So all the way down here, those are just your default. Okay, at least at this stage, those are just default. These are your primary planes. And this is your material, which you don't need to worry about it at all in this class. And that's your coordinate system. So you can always have more planes and more coordinate system. However, the default cannot be changed, is always there. And the later on added plane or coordinate system, they're gonna be at the bottom, like they're gonna be below the defaults. So starting here is your first feature. So pretty much if I drag this blue bar above this first feature, you're gonna have a clean workspace, like nothing. Right? So this is how you pretty much first open up SolidWorks and trying to create a model. You have nothing but a 3-plane and the coordinate system. And then you start making a feature at the first feature, which whoever made this model decide to use the base plate as the first feature. And I want to point out is this sometime there are more than one way to make a model. You can use multiple features and make a model, or if you're experienced enough, you can just use one feature to include all the other features. And this modeler or this drafter decide to work off from the bottom plate first, which in my opinion might not be the best practice, because sometimes we make the model in a machinist mindset. So if you're a machinist, you're trying to make this flange, are you gonna pick a plate like this to work on? How many people would take a plate, use this to make a flange, what I just showed you? Right? So, yep, you won't, because if you're trying to make a hub, you need to add material to it. Now, how can I add material to it? Either bolt it on or weld it, right? And that's really costly than just machine it. But anyway, this introduce the second feature, which is another extrude. So is a thicker and smaller plate that forms the hub. And the third one is a through hole. So which is the bore. The fourth one are 4 more holes, which are the bolt holes, the bolting holes. And then a chamfer. Sometimes if you have either interference fit or have a really tight tolerance with your shaft, you want to put a chamfer, so when they install the shaft, it won't break the shaft edge. And the fillet, overall, just to remove sharp edges. So this is some nice thing to have when people handling this part, won't get hurt. Okay. So tell me, anybody, if you want to make this part, how would you make it? You don't have to, say any feature or something. You can just let me know by your own words. You guys are all expert, huh? I feel like I'm wasting time right here. I'm just kidding. Yeah, you guys are really good. Yep, that's the answer I want to see. So I open up a new part. Let's trying to do a little bit to for the flange. Oh, I don't even remember the dimensions. What's that? 5.5, 2.75. Okay. Okay, so you select the front plane, and then from here, you can make normal to it, normal to, or you just click sketch, and that will make a normal view to it. Or you can select other planes, doesn't really matter. And normally my habit is when I deal with symmetric part, I start with the center line because they're going to be symmetric, right? So I'll draw two center lines. And now I can see the center lines are dashed line, which means they don't have any actual meaning to the model. It just pretty much give you a reference. Same thing as a straight line. And you make it construction geometry. So you make it construction line, it will become dash as well. And it will not be an edge anymore. Just give you a reference where that line is or something, you know? So after you make the two center lines, we're gonna work from one of the quadrant because eventually we're gonna revolve it with respect to one of the axes, which is the center line, and form the circular shape of that flange. So if you look at the cross-section view from here, pretty much it formed by two rectangles, right? Pretty much a big L. And let's make it L first. And you can, by using rectangle feature, so that's one, that's the bottom of the L. And we start from this point right here. So that's another L right there. And since we don't want this line in the middle, we want it to be an enclosed area. Let's just get rid of this line. Okay. And there's a corner feature. So trim entities, and there's a corner right there. So that way you can connect these two lines as a corner without any interference or extrusion. What do you mean? How do you geometry lines again? You mean from here? How do I draw the lines? Yeah, so here have line, circle, rectangle. So just pick anyone that can fulfill your idea. And now you can see the big L is all blue. Blue means underdefined. You can see underdefined right here on the bottom side of the bar. And now we need to define it. And you click on the smart dimension. So you can make all the dimensions now. So once I made a dimension, you can see this blue line turns black. That means it's fully defined. And you can change it anytime. So 2.75 minus 1.5, that's 1.25. Right. Okay. I feel like I can't calculate anymore. The 1.25 over 2. Right. And what is that? So it'd be 2.25 over 2. And 5.5. 0.75 and 2.25. So if you want that line to be mating, you can put 0. So 0.75 and 2.25. Look a little bit strange. 0.75, 2.25. I think I did the opposite. This one should be yeah, I think I did it wrong, but anyway, just to show you how to revolve it. So after done, the L turns black, means fully defined, right? We can either access sketch here, access sketch there, or just go to feature and revolve. Since we already have the axis being made, we can just revolve it. And it's gonna ask for the axis of revolution. Click this line, and pretty much you can see the preview of the flange. And this is based off the 360 degree. And you can change it to something like, for example, 90. You can see a quarter of the flange. So it depends how your sketch is. You can have like 2 portions of the sketch and do 180 degrees rotation, or only have 1 quadrant sketch and do 360. It's up to you. Okay. So this is how that flange gonna look like with the revolve. And now we need to add the holes, right? So it was an extrude cut before, even though we're supposed to use hole wizard, but the whole the whole wizard has the built-in information or the built-in specs of those ANSI, ASME, those common hole specs, and even with threaded, all this other feature in it. But for now, let's just use the extrude cut to make holes, because it will be easier for you. We're gonna have a separate section go over hole wizard. So extrude cut, once you click it, you click the extrude cut, it's gonna tell you to select a surface or a plane, and depends where your hole want to be. You can either go from this direction or go from that direction. Let's just pick right here. So now you're in sketch mode, and for some reason it didn't turn like the normal view. So let's just manually turn it. And every sketch you're making is on that plane. So let's draw the center lines since the holes are symmetrical as well, right? So sometimes if you don't know how to start or where to start, draw the cross of the center line first, and you know, it might help you. And you can always extend it, dragging it. Okay. So now we know that the 4 circles or 4 holes must be like 90 degrees apart, right? So we can just drag it along the center line and let it fix there. And it's still blue under define. We need to define its position. So from origin to this origin, we know the diameter is 4.25. Let's do 4.25 divided by 2. Also, how big was the hole? Half. Okay, so now it's fully defined. We have a hole here. And how do we make 4 of them? Let's do the extrude cut. So now see the previews of the extrude cut is right next to it because the depth we're doing is only 0.1 inches. So it has a different option here. Blind means it only go till certain point, which is 0.1 inches. If we change it to 5, you're gonna go all the way through because this thickness is not even, it's only 3/4, right? And we can do through all. Through all means all the subject in line of this hole will be throughed. And or we can do throughout both. That means it goes bi directions. So normally either the most common is either blind or up to the next up to the surface, or meet plane, or through all. So just remember these 4, it should be enough. Yep, so this will be a through hole going this direction up to the surface. So if I later on I want to add something on this side, the through hole will only stops at the bottom surface of this. It doesn't go through furthermore. Okay. And direction 2, we don't even need it. So just cancel that. So now you can see the preview is giving you a through hole. We click OK. We have 1 hole right here. And to make it 4, we're gonna go to pattern. So every feature is named pretty commonly based off humans' common sense. If you think like, okay, I'm gonna make a pattern, always use this search bar to search the feature that you can't find or you just didn't see on the manual here. So for example, I want to make a pattern. There's so many different patterns along the way. Well, this case, circular pattern works the best. And also this I symbol shows you where that command is. So click on that. They're gonna move your cursor automatically to there and tells you where that circular pattern can be found. So click on that. So the feature and the phases, we need to select this hole, right? And if you misclicked it or whatever, there's a drop down list right here. You can always select the feature right here. We'll select this feature and direction. Choose this direction because it's circular, right? We need to choose a circle. And this number means how many holes you want in total. We want 4 holes in total. And degrees apart, 90 degrees, right? Because it's 360 divided by 4. And that gives you 4. And also this is total number. So make sure you enter it correctly. Okay. So I highlighted the circular pattern. You can see all 4 holes being highlighted, just one in a different color, is because all the other 3 holes are made by this hole's specification, because is based on the pattern is based on this hole. The other 3 are just patterns. So every time you change in this feature, like if you change it to a little bit bigger, don't forget Control Q. This light means the part is not fully resolved. So Control Q, that fully resolves it. You change the base hole, you change all the pattern holes. And you want to change the pattern hole, sorry, you can't do it. You have to change from the base hole. And now we have chamfer. It's the same. I couldn't find where chamfer is. Type it in and get a chamfer. And now items to chamfer, location was here. So select this edge, not the entire surface. So select this edge, you can see the preview. This chamfer is really, really big. And if I remember correctly, that's 80,000. And if you want to do multiple chamfers, you can do it here. This is a selection window. Just keep clicking the edges that you want, you know. And if you don't want it, just clear section and click on the edge that we originally wanted. We have a chamfer. And there's a chamfer right here or right there. It's supposed to be right here. Huh? Nope, I remembered wrong. Yeah, that's right, because the pipe goes through this direction, not that direction. So the last feature is a fillet. Did I miss? Oh, yeah, it's 2L. My spelling sucks. So once we have the fillet, same thing, same theory of the chamfer. Just click, click, click. Yeah, that's a mating surface. We don't want a fillet over there. What was a fillet? This note right here, all fillets and rounds are radii of a quarter. So let's change this to a quarter. And yay, we just made the flange with a slightly bigger hole. Any question before we move on? Recording is going to be uploaded to onto Canvas. Anything about this model? I mean, the logic of how to make it should be clear, right? Pretty much, because it's symmetrical. We first consider use revolve, and then we add the features onto it. And if the features are symmetrical, we can either use mirror or pattern. No question? No question. I'm going to move on to make something else. All right, let's start with a brand new page. And still, this time let's select right plane. Don't really care. Let's sketch something. Let's make, well, before we make anything, make a center line first, because we're going to revolve it. Actually, revolve is a very powerful tool than extrude, because actually out there are a lot of parts that can be made from symmetrical. And even they cannot be making symmetrical, you can make this a symmetrical outline first and then modify it into its own features. Okay, we have our center lines. And now we're gonna work something up the center line. So if I choose the center rectangle and just draw a rectangle right here. Okay, so for example, if I define this rectangle and revolve it respect to the x-axis, what I'm gonna get? Everybody? Cylinder. It will be very flat though. Actually, yeah, exactly. I'm gonna get a washer, right? It's gonna be very close to a washer. It depends how big it is. But I'm gonna define it. Wow, I shouldn't define this way. Okay, let me define it first. And if I make some groove on the top and also some other things, I want to turn it into a pulley, which can be driven by V belt. Let's just make the feature from here to make the V groove of the belt. So pretty much simply 2 lines. And I stopped here because I want to show you guys how to use the mirror feature. So you hold your control, highlighted these 2 lines, and there's a mirror entity. And if you're not sure, you can just type in mirror, and they're gonna give you dynamic mirror entity or mirror entity. In this class, you won't be able to use this one. And let's just use the mirror entity. And since you already select those 2 lines, you don't have to deal with this box anymore. And mirror about. Now we can select the center line that we just created. And we click that. They're gonna give you they're gonna give you a preview. And this pretty much look like the V-shaped groove that our belt gonna fall into. And we click done. And now we can define those like the angle, the distance, whatever. And you can even drag it. The benefit of using mirror is because if I drag this point, the other side would change the same, just like a mirror. If I didn't use mirror entity, I just draw the line like from here, boom, 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 like that. I drag this line right here, that side is not gonna move. The mirror entity gave you a relation right here. So this is moving, and also that side would move as well. So those little blocks are the relation that constrain the position of the sketch. So define it or not is not really important because we just get a shape we want it, right? And make it narrower. Yep. All right. So once we make this line, you can see now this line became part of the enclosed area, right? So if I revolve right now, it's still gonna give me a washer because these lines are not like edge line. It's still within this rectangle. So we need to trim it down. So trim entities, and here's a power trim. So you just hold your mouse, the left button, and drag it. So you can see some lines are removed. So now we have like this geometry, and let's revolve it. And select the line of revolution. Since we only have one geometry, you don't have to select the contours. If you have multiple geometry, they will ask you to select which contour you like to be revolved. And here we go. We have a pulley with a very small center hole. If you like to do modification to it, so click on the drop down. you can edit the sketch. And always go to the normal so you don't misoriented any of the sketch. Weird. So for example, I want to do some material reduction from here to here. And I'm going to use a mirror again because I want to have the same effect on the other side. And mirror about, so pretty much the same thing as mirroring that two lines about the center. And here we go. And also trim the unnecessary lines. So we got a shape to look like a range. And from here, we can just axis sketch because we already have the revolve feature that gonna be driven by the sketch. We just axis sketch. And you can see the changes are already being reflected on your model. And same thing if you like to, change the hole. You double click on the dimension, make it like 1.5, like twice as big. And it doesn't show you the change because we didn't resolve it. So Control Q, the hole got bigger. Okay, any questions so far? So you guys are all good to start making parts, at least to use the revolve feature. Okay, great. That's what I'm talking about. Okay. If there's no questions, I'm gonna show you some recommendations how you guys gonna practice. So I know some of you guys, the goal is to pass the certified test, right, or something. So there are some practice other than watching YouTube or watch LinkedIn Learning. Go on McMaster. This is a website that if you have a career in R&D that's gonna build prototypes, you're gonna use McMaster, Granger, Parker, like T connectivity, and Jags or some like these vendors a lot, because pretty much this is where you buy all the hardwares, all the fittings, adapters, and all that kind of small stuff. So the reason I want you guys to get on this website is, for example, you want to see a flange. You just type in flange, they're gonna give you all different kind, even flange connections for elbows and all that. This is, I'll say, 80 or even 90% of the prototype companies buying from. So those are industrial parts. Is no harm to learn and now get familiar with industrial specs and standards. So you're clicking anything random, just anything. You go on there, any size, you pick on it, like the part number, and you can even download CAD right here. You just need to log in. And going product details, it's gonna give you pretty much everything you need about this part. The dimensions and pressure ratings, and even for what fittings, what pipes, So the practice is to look at this 2D drawing, make your own model, 3D model. And then after that, you download the model from the website, compare it to yours to see where you made a mistake or they made a mistake. I really doubt it though. But this pretty much has every single party has its own CAD and is available to download just for free, and and also is what industry is using. So it's, just benefit from academic and also your future career. And you're doing like McMaster, you can go on Grangers as well. And the same. It's just it just the website gonna take a little bit longer time to load. Where's that CAD stuff? Yeah, sometimes Granger doesn't have CAD for certain parts. It's supposed to be right here. Anyway, so you guys get what I'm talking about, right? Just practice, make, one or two models every weekend, because we don't have any homework. All we have are 2 projects, and the projects I'm going to show step by step is pretty much no self practice. So use what you can use to practice more, because this is just a software, and the more you practice, the better you can get. You're putting 100 hours into SolidWorks, you're gonna be like a pro level. So this is all what I want to talk about. And any questions?
Hey, Professor. So I have a question.
Mhm.
So last class, when we downloaded the SolidWorks, I think you talked about how you're going to tell us to turn on certain settings. Are there any certain settings like we should turn on in the program?
Yeah, well, it's not that important. Oh, here. I'll just have a setting of units. Yeah, so pretty much change your setting to English units, but it doesn't really matter. Whatever you guys are making in this class, like is not going to be a machine, right? So as long as the magnitude are reasonable, is okay. So the 8-hour tutorial is LinkedIn Learning. It's from CPP website. So just go on CPP homepage. And right here, you're punching LinkedIn Learning and LinkedIn Learning SolidWorks 2021. Click on the first one and, just go in there. Hey. So once you're in this page, go SolidWorks 2021. The first one is the 8 hours one. Okay, let's link into the chat. Okay, any more questions?
Yeah, I had a quick question. Do we have to buy this course
Wait, by what course?
for the 8-hour SolidWorks training?
This one's for free as long as you're a CPP student.
Oh, okay. You just log in. Okay.
Yes. Yeah. That's what I did, right? Just log in with my CPP. The recordings will be on Canvas. Well, it does make a difference. The most different is you can't use this 2020 to open a 2021 SolidWorks file. And the other difference is pretty acknowledgeable. Yeah, so 2020 will be enough for this class, but if you want to get 2021, that's fine. Yeah, so if you have no question about the lecture, you're totally free to leave, and please have a good weekend. And if you have a question, you can stay here and ask me.
Thank you, Professor.
Thank you,
Thank
Professor.
you. Yeah, you guys have a good night.
Have a good weekend, Professor.
You too. Thank you.
Professor, I think that there's a little problem going on with my SolidWorks. I just noticed when I queued it up and tried like using it,
Mhm.
but for some reason my toolbar doesn't show up unless I like scroll my cursor over it, and then it goes away when I go back to like work on my project.
Right click it, and there should be some settings to fix it there. Actually, I never had that. Oh, like that?
I'm sorry, I went back into SolidWorks instead of looking at yours.
Yeah, just look at my screen, it's like this. Like no toolbar.
No,
yeah.
it wasn't even that. Like it was like it shows up,
Mhm.
but could I screen share to you or no on here?
Yeah, you can wait till just you and me, then you can share a screen.
Okay, because it's like weird. Like it's almost like the icons are there, but just like not showing up, if that makes